Oh, hello. Yep. Oh, okay. Careful. So we have some new people. Is that correct? People who weren't. Who's here that wasn't here this morning?
Well, one of our elders showed up a little late. And then actually, one whole row got here, another row right here. You can do a south right here.
No, I did. I had the hands up. Good. Excellent. Well, I'm glad you came. We all right? It seemed to get a lot of feedback here. Yeah. By popular request, we've kind of switched the order a little bit. We're going to do the radiometric dating stuff first. And so the title's a little bit different than appeared in the article or in the advertising, but it's the same talk, just with a different title. And in fact, what we're going to do is we're going to find that there's information from radiometric dating that indicates that the Earth is actually quite young. Oh, before we get into all of the details of that, we need to talk about some general considerations. In particular, what is science? There was a case in the U.S. where the American Civil Liberties Union brought a case on behalf of somebody called Kitzmiller against a school district to stop them from teaching intelligent design in the science classroom. And the judge who decided that case ruled that you could not teach intelligent design in the science classroom because science was about explanations in the world around us based on what we can observe, test, replicate, and verify. Now, as I pointed out this morning, what he was actually talking about was operational science, the kind of science that tells us how the world operates. That's the kind of science that we can observe, test, replicate, and verify. So it's verifiable by repeated experimentation. There's this other kind of science, forensic science or historical science, that's not verifiable by repeated experimentation because it's about something that happened in the past. In fact, it's a story about the past, which makes it history, that tries to explain what we can currently observe, test, replicate, and verify. And as I pointed out, that involves a lot of speculation, and the nature of that speculation will depend on the presuppositions of the speculator. And I think it's even legitimate to ask whether or not we should call that stuff science. Now, you might think that we creationists have constructed this partitioning of science to suit our own ends, but that's not the case. This is a non-creationist scientist, works at the University of Chicago, and he's one of the guys heavily involved in the Big Bang stuff, and he's the one, in fact, who coined the term dark energy. And he says the goal of physics is to understand the basic dynamics of the universe, that is, how it operates. It's operational science. Cosmology, his field, is a little different. The goal is to reconstruct the history of the universe. So he recognizes the difference between operational science and this historical science. In fact, he says cosmology is about history. A colleague of his, again, pretty significant guy, he was a co-founder of this Sky Survey. He says cosmology may look like science, but it isn't a science. A basic tenet of science is that you can do repeated experimentation, and you can't do that with cosmology. So, cosmology, according to these guys, really isn't science. Now, if you put those two together, and then massage the words, or do a little bit of word exchange, it's very interesting. You can get this. The goal of biology is to understand the basic dynamics of living things. Okay, I think we can all agree on that. Evolution, however, is a little different. The goal is to reconstruct the history of life on Earth. Then you go on and you say evolution may look like a science, but it isn't a science. A basic tenet of science is that you can do repeated experiments, and you can't do that with evolution. And while we've changed the words, I don't think we have changed the meaning at all. All right. How do you know how old something is? Well, I know how old I am because I have a birth certificate. So the most reliable way to know how old something is to have this written record from a reliable witness or recorded by a reliable scribe on behalf of a reliable witness. In the case of a birth certificate, the scribe is the registrar general, and the reliable witness would have been my dad or the doctor. Well, this is exactly what we have with Genesis regarding the origin of the universe, or Earth, or life on Earth. In that case, the witness is God. He was actually there. He was actually the guy who did it. And the scribe was Moses. Now, it's interesting to take a detailed look at I don't know whether you'll be able to see this. Oh, yeah. At a detailed look at the birth certificate, because you'll notice while I was born on the 6th of March, it wasn't actually registered until a few days later, and I didn't actually get a birth certificate until a few years later. So it's not necessary that this written record be produced concurrently with the events. It can be written after the event. So, what does this reliable record tell us about the age of the earth? Well, it tells us stuff like this. When Adam had lived to 130 years, he became the father of a son and named him Seth. And Seth lived 105 years and became the father of Enosh, and so on and so on. And if you follow all of that through, you can construct something like this, which is a picture of a page in the back of my Bible. And from this, you can work out that the earth is roughly 6,000 years old. The earth, the universe, is roughly 6,000 years old. Now, that's not the answer you get if you hop on the internet and do an age of the earth Google search. You'll get something like this. If you go to Wikipedia, it says, the age of the earth is. Notice they don't say the age of the earth is approximately, or is thought to be, or might be. They say it is. That is a very definite statement that lends the idea that they actually know. Then it says it's 4.54 plus or minus 0.05 billion years old, or 4.54 times 10 to the 9th plus or minus 1%. Now, you might think, whoa, okay, so maybe it's not exactly 4.54, but it's definitely somewhere between 4.49 and 4.59. If you subtract 0.5 and add 0.5, that's what you would get, or 0.05. But in fact, that plus or minus 0.05 has absolutely nothing to do with accuracy. It only measures repeatability or precision. So if you were to do the same, exactly the same experiment over and over, or measurement over and over and over and over and over again, you would expect some variation in the result. And that's what this records. But it doesn't tell you anything about accuracy. To understand the difference, consider the micrometer, which was a tool developed to very accurately and precisely measure the thickness of machined parts. The accuracy depends on the relationship of these two parts, and the precision depends on the scale on the thimble. Now, if somebody were to cut off a piece of this, it wouldn't affect the precision, because that has to do with the scale on the barrel. So you would measure the machine part, and you would get plus or minus a very tiny bit all the time, but it would be wrong, because the instrument hasn't been manufactured correctly. Or, I'll give you another example. Here's a couple of target shooters. Here's the first one. And here's the second one. Which one is more accurate? Pardon? Somebody said the second one. The first one, right? Because they got near the right place on the target. But this one has a much smaller dispersion. It's got a much smaller plus and minus, right? The shooter was much more precise, much more repeatable, but not very accurate. I think the first guy is going to get the gold medal. All right, let's take these two things and put them on here. Which one is the most accurate? Well, you don't know, because you don't know where the center of the target is. You don't know what the right answer is. So you can't infer from the dispersion, from the plus or minus, from the repeatability, that that is more accurate than the other one, because you just don't know the answer. Oops, that's what I said there. Okay, so if you go back to here, what we know is if they were to do the same thing many, many times, the result would vary a little bit. But we don't know whether the result is in fact accurate. They say the age is based on evidence from radiometric dating. So we're going to talk about radiometric dating. Now, the legitimate question is, does radiometric dating in fact prove that the Earth is billions of years old? Well, the unequivocal answer to that is no, it does not. Because science cannot prove anything to be true. And you don't have to accept my word for it. This gentleman, who's a pretty important guy, works for NASA, read an article in Science magazine, to which he took exception. So he wrote a letter to the editor, and he says, the title of the 6th May News of the Week story, at long last, Gravity Probe B satellite proves Einstein right, made me cringe. I find myself frequently repeating to students and the public that science doesn't prove theories. Scientific measurements can only disprove theories or be consistent with them. Any theory that is consistent with measurements could be disproved by a future measurement. I wouldn't have expected Science magazine, of all places, to say a theory was proved. The editors did a mea culpa. Bennett is completely correct. It's an important conceptual point, and we blew it. So if somebody tells you that radiometric dating has proved the Earth is 4.5 billion years old, they're wrong. If somebody tells you that science has proved that evolution is true, they're wrong. Because science cannot prove anything to be true. It can only prove things to be false. And based on what we talked about in genetics and biology before lunch, I think science has proved that evolution is false. Now, these age of the Earth measurements are based on radiometric dating of meteorite material, which seems strange. You'd think if they were going to measure the age of the Earth, they'd measure Earth material. But they use meteorite material because they have an assumption that meteorites and Earth were actually made at the same time from the same material, but the material on Earth might have been compromised by the fact that it was part of Earth, whereas the material in the meteorite has not been compromised and it's been out there wandering around through space. But that's an assumption, that we were formed as part of this nebular hypothesis thing, for which there are, in fact, a lot of issues as well. Then they say it's consistent with the ages of the oldest known terrestrial samples. Well, how do they know how old the terrestrial samples are? Oh, because they measure them with radiometric dating. Well, but then the micrometer might be wrong, right? They might be getting a result that's consistent, but since they're using the same micrometer, they might be getting consistently wrong results. And the same with lunar samples. All right, let's look at this radiometric decay stuff, radiometric dating stuff. It's built around a radiometric decay process in which a radioactive element transforms or decays into a stable element. They call the radioactive element the parent, and they call the stable element the daughter. Now, I happen to be the parent of 2 daughters, so I understand the radiometric parent part of this, radioactive parent part of this really well. Maybe the stable daughter part, not so much. This happens with a characteristic time called a half-life. That's the length of time it takes half the amount of parent that's present to transform into an equal amount of daughter. So it works like this. You start at time 0 with a certain amount of parent. I got 16 lumps here. After 1 half-life, half of those, 8, will have changed into daughter. So we now have 8 of each. In the next half-life, half of those 8 lumps of parent will change into daughter, and so on. Okay? And that's the way it goes. Now, across the bottom, you see I've recorded the amount of parent and the amount of daughter after each half-life. And if you calculate the ratio of daughter to parent, it looks like that. It's increasing as time goes on. So, for example, at the end of 3 half-lives, the ratio is 7. So we can actually work this out with an equation and plot a graph, and it looks like that. And if we put 7 on there and come across, it's 3 half-lives. So we can kind of, apparently, use this relationship, the ratio of the daughter to parent to daughter, or daughter to parent, sorry, got it the wrong way around, ratio of daughter to parent, to determine how long the process has been going on. Now, there are some assumptions built into this that I'll highlight here. One is that there is no daughter to start with. Okay, and then it only builds up over time. So whatever daughter we measure in the sample, we assume has come from the radiometric decay of the parent. We also assume that the rock, the sample which contains this, has remained what's called a closed system since it was formed. That is, nothing has been added to it or subtracted from it since it was formed. And we also assume that the half-life has remained constant for the entire history of the rock since it was formed. These are the radiometric decay chain, radioactive decay chains that are typically used to measure the ages of rocks. I'm going to start with this one because it's commonly used to measure the age of volcanic rocks. It has the transformation of potassium-40 to argon-40. Now that argon-40 is a gas. And so what the assumption is, this is another assumption, well, it's related to the no daughter present at the start assumption. The assumption is that when the rock is hot, the argon gas is expelled out of the rock. It's boiled out of the rock, if you like. So any argon you see in the rock is assumed to have come from the transformation of the potassium since the rock got hard. Okay? So that's that. The radio age then measures the time from when the rock solidified. Now, this is an instrument, right? These things we're talking about here, if you like, are instruments that are attempting to measure something. So in order to assure that they are being accurate, we should calibrate them against something that we know. Right? That's these guys that go around and calibrate the pumps that give you your gasoline. They make sure that when you get a liter, you get a liter. They've got a little container, they know it's a liter, and they go, shh, and it gets a liter. So we need to calibrate this instrument, and you do that by using it to measure the age of something you already know. And they did that with some volcanic rock that was produced by Mount Narahoe in New Zealand. It erupted a number of times in the past when people actually were able to see that. So they knew when these rocks solidified. They took samples of them, sent them away for potassium argon dating, and these are the results they got. If you put them on a little chart, they look like this. Here's the 2 results from 1949 eruption, here are the 4 results from the 1954 eruption, and here are the 2 results from the 1975 eruption. All with their error bars, the plus or minus bits that we talked about before that indicated the expected variation or repeatability in the measurements. So there's a group down here that are about 270,000 years old. There's a group around here that look like about 1 million years old, and then there's this one up here that's 3.5 million years old. And notice they're all way outside the uncertainties. So these would not appear to be measuring the same thing. This one's, okay. The right answer, of course, is way down here. Just a few tens of years. And this is not untypical. There are lots of examples where we know when a volcano has erupted, and the radiometric dates are wildly different. Well, this is traced back to these assumptions. The assumption that's wrong here is that there is no argon present in the rock when it gets hard. And to see the effect that has, if we go back to here and assume that there's some daughter element when the rock gets hard, when we start the clock, then that stays, right? So we have to add that to all of these other events, all these other times. That changes the numbers across the bottom, which also changes the ratios. So now, after 3 half-lives, instead of the answer being 7, the measurement would be 11. And if you go back to this graph and put 11 on it, you get the wrong age. So the effect of a little bit of daughter present when the rock forms has a big impact on the actual age. It makes it look older than it actually is. So that would suggest that we'd better not trust any radiometric dates from potassium argon, because unless we know the right answer, we can't be sure the answer isn't wrong. And it seems every time we do know the right answer, we get the wrong answer. Okay, so this assumption can't be trusted. So scientists developed another technique. They kind of scrabble around. I mean, scientists aren't dumb. They recognize this. So they want to find a technique where this is not a factor. And they developed something called isochrone dating, where in addition to the parent transforming into a stable daughter, which I'm now going to call the radiogenic daughter, that is, its origin is in radioactive decay, this technique works on makes use of the assumption that there is also another isotope of the same element as the radiogenic daughter that is naturally occurring and stable. Okay? And I call that the non-radiogenic sister. Then there's a second assumption. The way this technique works is that they take a number of different samples of the same rock, but they assume that they may not have the same initial composition. Or they don't require them to have the same initial composition, but they do assume that they all have the same initial ratio of sister to daughter. Okay, so it doesn't matter what the actual composition is, that ratio is assumed to always stay the same. So they've essentially replaced one assumption with another assumption. Okay, so that's that assumption down here now. Now what to do is they take all of these different rock samples, and instead of measuring the ratio of the daughter to parent, they measure the ratio of daughter to sister and parent to sister. And for a whole bunch of different rock samples, they plot this on a two-dimensional graph, and if everything works, you should see a straight line. And you can use the slope of the straight line to calculate an age. Now, it turns out that while potassium-40 doesn't work with this one, all of the other ones that are listed here do. So, for example, rubidium decays to strontium-87. Strontium-86 is a naturally occurring stable isotope. Samarium-147 decays to neodymium-143. Neodymium-144 is a naturally occurring element. And in lead, in the case of lead, there are two radioactive isotopes of lead that decay to two stable isotopes, or two radioactive isotopes of uranium that decay to two stable isotopes of lead, and there's a third isotope that is naturally occurring and stable. So these are all amenable to using the isochrone technique. So scientists got some samples, send them off, have them tested, and what we measure here is the relative isotopic abundances of these different things. And the repeatability with which we can do those is indicated by those little vertical black bars. And we plot these on a graph, and we get some pretty nice straight lines. And we use the slope of the straight line to calculate an age. And the plus or minus on the age is a measure of how well that straight line fits the data. So if you got very small error bars, it's a very tight straight line, and you get a very small uncertainty in the age. So you can see here we got ages in the range of 1.24 billion plus or minus 84 and all this good. So how does this work on this volcano in New Zealand? Well, not very well, actually. Rubidium and samarium decay chains give 133 and 197 million years old, and the lead gives almost 4 billion years old. Now somebody might point out, legitimately, that while the potassium-argon technique can be thought to be measuring the age since the rock solidified, these techniques might actually be measuring the age of the magma that was used to form the rocks, and that's a legitimate observation. But if that's the case, that magma should have only one well-defined age. So that means that all these three readings should agree within the uncertainties, and they don't. Not only that, the same should be true of these, because these are all using the same rock, just using different instruments, if you like, for trying to measure the age. So it's like you were trying to measure the weight of something using three different scales. And you got, like, they all measured plus or minus a milligram. And so you measure the weight, and you get three different weights that are different by several grams, or maybe even tens of grams. Okay? How do you know which one is right? Well, you don't. Because you don't know that any of the scales are actually weighing correctly. And that would be the case here. We don't know that any of these are correct. And if you look at them again on a little graph showing the error bars, and you make an assumption that they are actually trying to measure the same thing, in which case you can use those error bars to calculate the probability that that would be the case. For these two, there's less than 3 chances in 10,000 that they are actually measuring the same thing, and in this one, it's even worse. So, to kind of re-emphasize that, here we have 3 measurements using 3 different micrometers of the thickness of a machine part, together with their errors. 124 millimeters plus or minus 0.84, 165.5 plus or minus 0.4, and 188.3 plus or minus 0.53. Which is the correct thickness? You don't know. It's like when I asked you which shooter was closer to the center of the target. Well, you don't know, because you don't know where the center of the target is. You don't know what the right answer is. So here we are, the age of the rock. The same thing. Same numbers, just presented differently. What's the right answer? You don't know. There's quite possibly, they're all wrong. So, if you look at the isochrone technique, it doesn't work. It could be because the rock has not been a closed system, so either some of the uranium or some of the lead has been either added to the rock or taken from the rock during its alleged lifetime. Or it could be that the half-life isn't constant. Now, when I went to school, or it could be actually that this assumption is incorrect as well. Now, when I went to university, they taught us very specifically that the radioactive half-life, the radiometric decay rate, the half-life, never changed. Well, remember I said that science can't prove that to be true, but it could prove it to be false. It's done that. In the last little while, there have been observations that indicate that the half-life does change. We have here in the upper graph, cobalt-60. And you can see how the half-life, the radioactive decay rate, changes as a function of time. It's on pretty much on an annual basis. On the lower left, there's two other isotopes, silicon-32 and radium-226. So the half-life does change. Now, this observation, they aren't very big changes, but in effect, what they do is falsify that assertion that the half-life is always constant. What that means is that it could have been quite different at other times in the past. So if we go back to our assumptions now, we can no longer trust that assumption, and that's fundamental to these calculations. All right, so if looking back at this then, it looks like there's really no reason to put any kind of confidence at all in the answers given by any of these radiometric decay chains. There's one left, and that's carbon dating. You may have heard of that. It makes use of this particular decay chain when carbon-14 changes to nitrogen-14. Now, carbon-14 is not a naturally occurring isotope of carbon. That's carbon-12. Carbon-14 gets manufactured in the atmosphere when cosmic rays bang into things in the upper atmosphere. It's what's called spallation collisions. They just kind of break everything apart. Eventually they produce some neutrons, and these kind of wander around and get absorbed by nitrogen-14, which changes into nitrogen-15, which then becomes carbon-14. Carbon-14 is chemically just like carbon-12, which is the stable isotope of carbon. So it forms carbon dioxide. Carbon dioxide is plant food, so plants absorb this radioactive carbon dioxide as part of the photosynthesis process and incorporate it into the plant tissue. So that means all of those beautiful trees and flowers and stuff that you see out there every day are radioactive. This, to me, is probably one of the best arguments I've ever heard for not eating Brussels sprouts. Okay, so all the plants are radioactive. Animals don't know this. So they come along and they eat all of these radioactive plants. They incorporate carbon-14 into their tissue, so they become radioactive. So this means, unfortunately, that our steaks are radioactive, and I'm not giving up eating steaks. So we eat all the fruits and vegetables and steaks and stuff, and we get carbon-14 in our bodies as well. But while we're living, we are replacing the carbon-14 that is decaying with new carbon-14 that we eat. Same with everything else. But when we die, that stops. Right? So when the... I forgot to put that up, I'm sorry. When the organism dies, there's a certain amount of carbon-14 in its body. And it's decaying, and it doesn't get replaced. So if we start with this amount, after one half-life, half of that will have changed, and it changes back to nitrogen-14. Then after another half-life, half of what is left changes to nitrogen-14. Now, biological tissue decomposes. Trees rot, animals decompose. And so the nitrogen, being a gas, gets back out in the atmosphere, so we're left with this. So we can't use that technique before of measuring the ratio of daughter to, or a parent to daughter, or daughter to parent, because, if you like, the daughter's left home. However, in the sample, the stable carbon-12 is still there, and it doesn't change. So if we can measure the ratio of carbon-14 to carbon-12 on the right-hand side, and we know, or knew, what the ratio of carbon-14 to carbon-12 when the organism died on the left-hand side, and we know the half-life of carbon-14, and it hasn't changed, we could potentially calculate how long it's been going on, this process, since the sample died. And that's exactly what goes on. They measure the ratio on the right-hand side with special instruments called accelerator mass spectrometers. They assume that the ratio on the left-hand side is the same as the ratio of carbon-14 to carbon-12 in the atmosphere today. And they assume it doesn't matter when the sample died, that ratio has always been the same. That ratio is not very big. It's 1 atom of carbon-14 to 1.2 trillion atoms of carbon-12. Is everybody familiar with what a trillion means? You know, if you paid attention to the discussions about the US debt a few years ago, you ought to be really familiar with trillions. We're kind of getting to that point ourselves, but not quite yet. It's a big number. That's what's referred to as modern carbon. What they measure is a percent modern carbon. And they use these machines called accelerator mass spectrometers, which have a design sensitivity that will allow them to measure down to 0.002% modern carbon. If you do the calculations of the equations, that corresponds to 15.6 half-lives. And it doesn't matter what the half-life is, that's the ratio. Now, we measured the carbon-14 half-life to be just under 6,000 years. And it's assumed to be constant. So if you do that calculation, it means that after about 90,000 years, there is insufficient carbon-14 in the sample to be detected. So carbon-14 dating cannot theoretically give you an age older than 90,000 years. Coal we know to be largely carbon, and it occurs in just about every layer of the geological column, except those ones shown in red. Now, the U.S. Bureau of Mines maintains a data bank of coal samples from all the different coal mines around the U.S., so it's got samples in it from different states and all the different layers. Some creation scientists got some coal samples from that data bank from these 3 different layers, which, according to uniformitarian geology, would have ages ranging from about 37 million years to about 320 million years. Now, you will notice those numbers are all greater than 90,000. So that would mean there should be 0 detectable carbon-14 in these coal samples. Well, they sent them away to a carbon-14 dating lab. This is a place that does carbon-14 detection for a living. And these are the results they got back. We have percent modern carbon plotted along the bottom and the number of samples containing that amount of carbon-14 up the side. Here's the sensitivity of the instrument, so you can see it's well above the detection threshold. If you calculate the ages, it's around about this. Now remember, the geological age is in the tens to hundreds of millions of years old. The actual radiometric age is in the 50,000 years old. Now interestingly, this evidence, what we see, is what we would expect to see given the biblical account in Genesis. Right? If the coal is formed as a result of burying vegetation, that vegetation would have been growing before the flood. All growing in the same time period. So it would all have the same amount of carbon-14 in it. And that's what we see. We don't see any differentiation of the different layers. They're all the same. They all have the same amount of carbon-14 in them. On the other hand, the evolutionary account, there should be no carbon-14 in them. Now recently, some other scientists have sent some dinosaur bones to a radiometric dating lab using carbon-14, and they turn out to have the same amount of carbon-14 in them as the coal. Now, we're told dinosaurs went extinct 65 million years ago. So that carbon-14 should be entirely gone. In fact, if the entire Earth was composed of carbon-14, it would be entirely gone in less than 1 million years. So the fact that we see carbon-14 in dinosaur bones clearly indicates they are not millions of years old. And again, the results are consistent with what we would expect from the biblical account. If these dinosaurs were buried during the flood, that means they lived prior to the flood. So they were eating that vegetation that was growing prior to the flood, plus eating each other, but they would all have more or less the same amount of carbon in them. And that's what we see. And we see the same thing with diamonds, which are supposedly billions of years old. They got a bunch of diamonds and sent them away for dating. And here's the limit of the sensitivity. Now they're about 60 times, which is a little bit less than the coal, but because of the exponential relationship, it's not that much different in age, 55,000 years, as opposed to 1.3 billion. And this next bit of evidence is really quite fascinating. In Australia, they were digging a ventilation shaft for a new mine down through a profile that looked like this. And when they got down to the bottom, 69 feet down, they found tree trunks. The bottom of the tree trunks were buried in this sandstone that is supposedly 250 million years old. The tops of the tree trunks were in the basalt layer, and they were charred by the basalt. So they were there when the basalt came intruding. Now, they sent the basalt away for radiometric dating, and it came back at 45 million years. They sent the wood away for radiometric dating, and it came back at about the same age as the coal and the dinosaur bones. And again, that's exactly what we would expect. So we see all of these different things with carbon in them that supposedly have ages that are millions or hundreds of millions of years old, but they all have essentially the same amount of radiocarbon in it. Now, the number that we get here for the age, the radiocarbon age, is clearly different from what we would expect from the biblical account, but remember, the calculation of that age is based on this assumption about the ratio of carbon-14 to carbon-12 in the atmosphere. And I submit that that assumption is wrong. It's assumed that it's always been the same as it is today. And if we look at just ignore that little yellow arrow for a minute, it'll be clear in a minute. If we look at how much carbon-14 and carbon-12 there was in the atmosphere at different times in the past, we know what it is today. It's this amount. What about at creation? Well, I would submit that there would be no carbon-14 at creation. Remember, it's not a naturally occurring isotope. It's not required for life. It's carbon-12 that is the basis of life. So God has no need to create carbon-14. So that means it would have to build up in the atmosphere over time. And that means the rate at which it builds up is proportional to the rate that cosmic rays are getting into the atmosphere. That, in turn, is dependent on the strength of the Earth's magnetic field. The stronger the Earth's magnetic field, the more of the cosmic rays will be deflected back out into space. The fewer of them will get into the atmosphere, the less carbon-14 will be produced, and so it'll be growing up slowly in the atmosphere. Right? The Earth's magnetic field has been known to be declining at about 6.3% per century. If you put in 5% per century, that means that back about the time of the flood, it was 9 times stronger than today, and back about 6,000 years ago, 60 centuries, it would be 20 times stronger than today. So that would mean many fewer cosmic rays getting into the atmosphere, much less carbon-14 being produced today. So it would be increasing very slowly until it then, after the flood, increases more quickly. So it's not unreasonable to estimate that there might have been as little as 10% of the amount of carbon-14 that's present in the atmosphere today in the atmosphere before the flood. What about carbon-12? Well, we know how much is in the atmosphere today. What about at creation? Again, we don't know, but if we take this perspective that the coal was formed from vegetation, there was clearly a large amount of vegetation growing before the flood. That means a lot of carbon dioxide in order to support all of that growth. We know, for example, that if we double the amount of carbon dioxide in the atmosphere, we'll get 41% more plant growth. So given that there was a huge amount of more plant growth, we must have had a lot more carbon-14, or carbon dioxide in the atmosphere. In fact, if you look around on the internet, you can find that it is claimed that back in the Jurassic, which is the age of the dinosaurs, they say that the carbon dioxide level in the atmosphere was 4 to 5 times what it is today. And back 500 million years ago, which is just at the start of the Cambrian, which could be just around the time of the start of the flood, they say that the level of carbon dioxide in the atmosphere was 20 times what it is today. So it's not unreasonable to assume that it might have been 10 times what it is today. That would put it at 0.4% of the atmosphere. It's 400 parts per million today. And we know that even at 1%, it's not bad for human existence. It's not a problem for survival. So at 0.4%, it's not an issue. It's still okay. So that would mean that the ratio of carbon-14 to carbon-12 before the flood was maybe as small as 1% of what it is today. That means that fundamental equation, or fundamental assumption about calculating radiocarbon ages is wrong, and they should all be quite a bit smaller. In fact, if the ratio of carbon-14 to carbon-12 was 2%, then the number that you would calculate would be 5,000 years old. Now, with respect to carbon-14 dating, this I think is very telling. That's by not an archaeologist, I can't remember. Anyway, he says, if a carbon-14 date supports our theories, we put it in the main text. If it does not entirely contradict them, we put it in the footnote. And if it is completely out of date, we just drop it. So this is an example of what's known as confirmation bias, or cherry-picking the data. In other words, they'll pick the data that they get that confirms the result that they want. Now, the real travesty of this, from a scientific perspective, is They'll publish this paper. Somebody else will cite this paper without knowing that they did this. And somebody else will cite the paper not knowing that they did it. Somebody else will cite those other papers. And eventually this becomes received wisdom. And in fact, it's been a manufactured result. Now I'd like to touch on one other aspect. So far what we've seen is that we cannot really accept the dates from radiometric dating because there's too much evidence that they're incorrect. And in the case of carbon-14 dating, there's some indirect evidence. I mean, qualitatively, it supports the biblical account. And there is a mechanism for establishing that quantitatively, it also accepts or agrees with the biblical account. But that's a little bit like the just so stories that Dr. Lewinton talked about. With radiogenic helium dating, we have an actual measurement that supports the 6,000-year-old age of the Earth. That has to do with things called zircons. Zircons are crystals, and when they solidify as crystals, apparently, they do so in a way that excludes lead, but includes uranium. So they have inherent to themselves an approach of trying to get to that assumption of no radiogenic daughter present at the time the crystal was formed. Now there have been some experiments lately, or some discoveries, observations lately, that say, well, that's not quite entirely true, but let's go with that. So uranium-238 gets incorporated in these zircon crystals, and it decays to lead-206. In doing so, it emits 8 alpha particles. Alpha particles are helium nuclei. And those little red things are electrons. And so these helium nuclei latch onto these electrons and become helium atoms. And helium is a noble gas, doesn't form any compounds, and leaks out of everything. So it will leak out of these zircon crystals. So every time a uranium atom changes to a lead atom, we get 8 helium nuclei that should start diffusing out of the zircon crystal. Now, some creation scientists got some zircon crystals from... Oh, so this is what's going on, right? So the uranium decays to lead, and we get all of these helium, these 8 helium atoms produced, and then they start diffusing out of the helium zircon crystal, and then we have another uranium atom decays to lead, and so on and so on and so on. Now, some creation scientists got some zircon crystals from the Los Alamos National Laboratory, who were drilling a big deep hole in New Mexico, and they looked inside and they found some uranium and they found some lead. Based on the ratio of lead to uranium and applying the previous things we've talked about with radiometric dating, they calculated that these zircon crystals would have been 1.5 billion years old. Given the amount of lead that was there, there should have been this, well, there would have been this amount of helium produced. If the crystals really are 1.5 billion years old, essentially all of that should have diffused out. That's a very long time, and the helium would have leaked out. But in fact, they found up to 58% of the helium that had produced was still there. So one of the scientists said, I think what I'll do is I'll do a couple of calculations on the rate at which helium diffuses through zircon. I'll do one of the calculations based on the assumption that these crystals are actually 1.5 billion years old. And I'll do another calculation based on the assumption that the zircon crystals are actually only 6,000 years old. Now the shape of the curves is pretty much the same. And you can plot them on the same piece of paper because it's an exponential scale on the left-hand side, but they're actually different by a factor of 100,000. So it's not like they're very close together. They're really dramatically different. So they thought there might be a way to test this. If we could actually measure the diffusivity of helium through zircon, we could maybe distinguish between those two. So they went to Los Alamos National Laboratory and said, could we please have some more zircon crystals? They said, sure, here are a few more. Same hole. And they sent them away to a laboratory, actually I think it was in Guelph, Ontario, to measure the helium diffusion rate. And these were the results. They fit exactly with the prediction based on the assumption that the zircon crystals were 6,000 years old. Now, as you noted, probably from the words, the predictions were done 3 years before they got the results. So people often say, well, creation science can't actually make any predictions that can be confirmed by experiments. Well, that's not true, because here's one of them. If they redid the calculations to get the best fit for the data, the age that they got was 5,681 plus or minus 2,000. So this illustrates the difference, again, between accuracy and precision. This is an accurate result because it's close to the right answer, but it's not very precise because it's got a big uncertainty in it. Now this raises two possibilities, actually. Either the diffusion rates have been dramatically lower in the past so that the helium couldn't diffuse out, or the radioactive decay rates have been dramatically higher in the past. Now the second one of these would have been anathema before we had those observations that radioactive decay rates do actually change with time. So if we take a look at radio halos, we can get an idea of which one of these might be correct. Remember, uranium decays to lead. It gives off these alpha particles. Alpha particles have a particular amount of energy. Each one of those alpha particles has a different amount of energy, but a very well-defined amount of energy. They bang into their surrounding crystal structure and give up their energy, but in doing so, they cause dislocations in the crystal structure, which can show up under the proper treatment as discolorations. And they lose their energy in a very particular way. They lose a little bit of it for a long time, and then all of a sudden they lose a whole bunch of it. And these places where they lose a whole bunch of it form concentric spheres around the source. So when you cut through those, you'll see circles, and these are the halos. Here is a set of halos from radioactive decay of alpha particles, and if you count them up, you find out there are 8. That means this is uranium-238. The zircon crystal is right in the middle. Now these radio halos generally occur in something called biotite, which is flaky material like mica in granite rock. And if you plot a graph of the density of radio halos as a function of the depth of the rock in which they are found, in this case it's plotted as age, that is the geological age associated with that depth, you'll see that they concentrate in one particular range of age/depth. If you were to interpret that depth in terms of a biblical flood model, these would be, in terms of the normal geological layers, these are Precambrian rocks. These are these kinds of rocks, and then these are tertiary rocks. But if you interpret it in terms of a flood model in the Bible, these would be pre-flood rocks. These would be flood rocks, and these would be post-flood rocks. So the flood lasted for, remember, about a year. So the fact that we see all of these radio halos concentrated in that 1 year indicates that there was a very large amount of radioactive decay going on during that year. And so this observation of the concentration of radio halos provides some support to the idea that the radioactive, if the two of those two things, the one that is correct, is that the radioactive decay rate was much higher during the flood. Now it's interesting to point out, that there really is no way you can distinguish these two ideas about standard decay rate and accelerated decay rate by looking at what we can see today. Here is what the amount of uranium would be as a function of time before the present, going back 4.5 billion years, if the decay always happened at the same rate. So here's the present over here. If we started with the quantity 1, 4.5 billion years ago, today we would have about 50% of it left, according to the geological timescale. If we now say, well, but what if the Earth is only 6,000 years old? We started with the same amount of uranium, and it decayed at the current rate until the flood, and then it decayed really fast, and then it went back to decaying at today's rate. That would look like this. We overlaid the green, which is that, on the standard blue. So over here we have the present. We have exactly the same ratio of 206, or same amount of initial lead still present. Back here, we have the same amount of lead as would be present in both cases. Back here we have this, and we have here, and we go along there at the same rate, and then we have this period of accelerated decay to get to that. And since the flood, the measurable quantities, which are the relative isotopic abundances of those two approaches, would be exactly the same. So just simply based on measuring those abundances, you cannot distinguish these two. But with the zircon crystal, with the radiogenic helium and the radiohalos, we can. We're using evidence from a different perspective. So, in summary, radiometric dating depends on a lot of assumptions that I think we've demonstrated are incorrect. It gives ages that don't agree with known ages. It gives ages that do not agree with each other within the asserted uncertainties. We have carbon-14 in coal, diamonds, dinosaur bones, and charred wood that contradicts the assertions of millions and billions of years. The difference between the ages that we get when we calculate them using the normal approach and the biblical expectations is rationally explained. That was the ratio of carbon-14 to carbon-12. And then we have this helium diffusion in zircon, and there's another set of diffusion measurements of argon and feldspar that gives the same results. They give ages consistent with the biblical time frame. And these are completely independent of any of those assumptions built into radiometric dating. The only thing they depend on is the fact that when uranium decays to lead, it produces 8 alpha particles. And after that, it uses a physical property of a different material to interpolate to get to the age. So again, to go back to my initial question, no, radiometric dating doesn't prove that the Earth is billions of years old. In fact, it gives evidence that the Earth is only a few thousand years old. All right. I think I'm just going to run through some resources. But, if anybody's interested in pursuing this kind of stuff in a little bit more depth, that particular book, which is on the table, has a lot of additional detailed information in response to specific questions people have asked, that you can pursue that. There's also a DVD back there that is essentially this talk in a previous incarnation that I gave at a super conference that you can get for nothing if you sign up for Creation Magazine. How's that for a deal? Magazine itself is a deal, and you can get that DVD for free. All right, thank you very much, Pastor. Dinosaurs will follow after a break.
Maybe if you could just spend 2 minutes telling us about your own conversion. You were an atheist, and then did you pursue your PhD studies while you were an atheist, or were you a creationist at the time, Rudy?
The former.
Just take us through that sequence. I think the people would like, they look at you and say, this guy's got a lot of knowledge. Tell us just a little bit about yourself.
Oh, I'll try. A little bit, that's always hard for me, because you've probably noticed I like to talk a lot. I grew up attending church in what is referred to these days as a mainline Protestant denomination. I attended that all through until I graduated from high school. And as far as I can remember, I don't actually remember ever hearing the gospel message coherently presented. Now, that may be because it wasn't, or it may be because I simply wasn't paying attention. I don't know. But anyway, by the time I graduated high school, when the convention was to join this church, it seemed more like a social club than anything else to me. And I was going off to university, so I thought, well, there's no point. So I didn't. So I went to university. I took geology in my first year engineering. And of course, they taught us all about the geological column and how it represented hundreds of millions of years. And I subscribed to Scientific American, so I read all about the Big Bang and biological evolution. By the end of maybe October, of my first year, I figured I had the answers to all of life's big questions, and none of it required a God. So I became a confirmed atheist, although I recognize atheists don't have confirmation services. But although they now have a church in the U.S., so maybe they will have soon, I don't know. Anyway, I stayed it was an intellectual decision, right? I mean, it was a conscious thing. It wasn't, I just didn't drift into it for lack of something better to do. I made that decision. And I stayed that way until I was about 30. And then I was married by this time, had 2 children, daughters, if you remember. Something happened in our lives that wound up, long story, but it wound up with me having to confront the question that C.S. Lewis, I guess, posed: was Jesus a madman, a con man, or the God man? I'm an engineer by this time, so I figure, you got to do this right. You got to do it based on evidence. You got to do it with rigorous logical reasoning, yada, yada, yada. So I did that, and when you do that, you come to the conclusion that he was who he said he was. He was Son of God, come to earth. So you would think this would be an excellent time to become a Christian, right? Well, I decided I'd join a church instead. I joined another mainline Protestant denomination that I attended for another 10 years and never heard the gospel. And this I remember. I can remember sitting in church thinking, why aren't these guys preaching from the Bible? Preach from all kinds of other books, but not the Bible. So that went on for another decade, and just before my 40th birthday, some friends of ours invited us to go to a Bible-believing, gospel-preaching church where I heard the gospel, and after several weeks of arm wrestling with the Holy Spirit, finally got saved. However, I still didn't make the connection between the gospel and the creation account, the Genesis account. And it wasn't for another 10 years until I went to something not unlike this, actually, only it was Friday night and Saturday, when two guys from the Institute of Creation Research came and did this kind of thing. They would tell us of how everything we see in science is just what you would expect to see. You just read the Bible like history, right? And it was like, aha. You know those commercials about the aha moment? It was, aha. Now everything makes sense. I mean, between the time I got saved and this happened, I kind of didn't let anybody know I was a Christian, because I knew, sort of, I think, subconsciously, that there were all sorts of really easy questions they could answer that I would not be able to answer. They could ask that I would not be able to answer. But once I kind of had this aha moment, the answers started to appear. I mean, there were answers to everything. The answers book has answers to the 60 most frequently asked questions that people make. There are answers to all of this. And all of the scientific evidence that we see is just what we would expect to see, given Genesis as history. That's really cool.
All right. We're going to take about a 5 or 7 minute break, and then it's Dinosaurs. That's our last session. So let's take a little breather and then come back.